All right, good morning, everybody. Thank you for joining me today. My name is Mike Ryan, and I have been researching Bluetooth and Bluetooth security for about 7 years now, and I wanted to bring together everything I learned over the time doing that into a learning talk about how to look into Bluetooth and how to start learning how to hack it. I will say this talk is not going to be like, here's a bunch of awesome Bluetooth vulnerabilities and like we hacked all the things. This is really going to be more focused on learning how to do Bluetooth reverse engineering and Bluetooth hacking. But some people in the audience might be asking yourself, why Bluetooth? It's not necessarily the most headline-grabbing technology. There were some vulnerabilities recently that came out, like Google's Titan security key and all that sort of thing. But it's, on average, not the most exciting topic. I will point out, though, that the growth has been pretty impressive, 12% year over year. And these numbers come from the Bluetooth people, the Bluetooth SIG, so take them with a grain of salt. But it's definitely a growing technology, if not the most exciting technology. However, when it comes to the security of Bluetooth, it's a little bit of the Wild West. And I was asking myself, why is this? Why is there a relatively low movement in the Bluetooth security space relative to other wireless technologies or web technologies? I think it's partially due to the fact that Bluetooth is somewhat inscrutable. It's a little bit weird of a protocol if you're familiar with others. And I think it's partly because people think it requires super specialized tools. You can't just pop open Wireshark and sniff Bluetooth the way you can with Wi-Fi or Ethernet. So I want to dispel the notion that Bluetooth is mysterious or unreachable. It's actually very possible to get into Bluetooth right now with tools that you already have, and that's what we're going to be focusing on today. Who is this talk for? Bluetooth device developers. If you're developing a Bluetooth device, you probably want to keep security in mind, and you want to have an understanding of what security risks are out there for your device. If you're a penetration tester and you come across a Bluetooth device, where do you even begin? We're going to get into that. And finally, if you're a manager, if you're a product manager or you're managing a team of engineers, do you have the skill set on your team? Are you taking the right steps to ensure that your device is secure? So the structure of the talk, I'm going to give you an overview of Bluetooth. I promise I will keep it pretty brief. Then we're going to talk about the reverse engineering process and tools. And finally, we're going to go over case studies. I'm going to walk through actual devices that I did security analysis on, reverse engineered, and show you the exact steps I took, so hopefully you can learn how to do that and do it yourself. So to start, let's talk about Bluetooth and the reverse engineering process. We're going to start with a very, very high-level model of a Bluetooth device, and it doesn't really matter what kind of a device we're talking about. In this case, we're going to be focusing on a Bluetooth wristband, like a fitness wristband, something that tracks how many steps you take. And normally, those devices have a smartphone app that they communicate with. And the way it works is sometimes you do something in the smartphone app, sometimes you might press a button or tap the device, and those two devices will establish a connection via Bluetooth and communicate. And that's the part that we're really interested in, right? We don't care about anything else. We just care about what kind of Bluetooth is happening. And I will note, the same is true if your Bluetooth device communicates with a laptop. Simple enough, right? So how do we actually begin reverse engineering it? Where do we start? The first step, you do something with a device in the app, and you make a note of what you do. For instance, if it's a fitness wristband, you might take a bunch of steps, you might tap the synchronize button, and then the number of steps gets synchronized back to the app. And you'll say, oh, I took 5 steps. The second thing you do, capture the data sent via Bluetooth. Once you have that data, you analyze it. You can really understand how the device works. Super high level, makes sense, right? But we get stuck here on step 2. How do you capture the device? How do you capture the data sent via Bluetooth? That was what I was alluding to earlier in the talk. You can't just pop open Wireshark, right? So can I get a show of hands? Who here thinks that we should sniff the Bluetooth? Oh, okay, yeah, all right. People are waking up. I have bad news. Sniffing Bluetooth is hard. It's hard, but it's not impossible. This device is made by a company called Elysis, and there's another company called Frontline who make a really similar device. This is a commercial, professional Bluetooth sniffer. These devices are supposedly really excellent. I haven't used one, but they're 100% reliable. If you want to sniff Bluetooth, this device will do it. Unfortunately, it comes at a small cost. The starting price on this and the competitor from Frontline is around 20,000 bucks. That's out of most people's budgets. I will, again, make a disclaimer. I haven't used this. This is not an endorsement of this product. But from all accounts, if you want to sniff Bluetooth, this thing is the business. On the other end of the spectrum, you might be familiar with an Ubertooth One. This is a much more affordable tool. It's in the $100 price range, so within most hobbyist budgets. Unfortunately, it is not reliable, or I wouldn't say unreliable, but it's nowhere near as reliable or as useful as the commercial Bluetooth sniffer, and it is limited to BLE. And we won't get into it now, but there are different Bluetooth protocols, and if you want to sniff something with classic Bluetooth, this device won't do anything for you at all. Unlike the Elysis Bluetooth sniffer, this is an endorsement. I wrote most of the BLE sniffing firmware for this device, and it's actually pretty good at that. I also will say I don't make this device and I don't get any kickbacks. I just think it's pretty cool. But what if I told you there is a better way? We don't have to spend 20 grand. We don't have to futz around with kind of dodgy open source software. And in fact, you might already have a device that already does this. If you have an Android phone in your pocket right now, if you have a laptop running OS X, or if you're a Linux nerd running Linux on your laptop, you can actually get the Bluetooth data that you need to perform this kind of analysis. How does that work? Well, let's go back to our model of the Bluetooth device. You've got your two devices, they're communicating via Bluetooth, and the sniffing approach is that we want to capture the data here as it's going over the air. Well, the data already exists on our smartphone, and this is a smartphone that's running an operating system. We have a lot of control over that device. So wouldn't it be great if we could sniff the data on the smartphone before it even goes over the air? And that's exactly what we're going to do. Before I go into the mechanics of how that works, I'm going to give you a little bit more theory, because this is going to be relevant to when we're looking at the data. I know some people went cross-eyed when they just looked at this. This is a simplified version of a Bluetooth stack. And don't worry too much about what the various layers mean. I'm going to put up this rough equivalence here. If you might be more familiar with the TCP IP stack, and if you squint really hard, the layers of the Bluetooth stack match up with the layers of the IP stack. So at the top, you've got the app layer. Think of it like HTTP. This is where the actual data that you care about lives. And then below that, you have layers that are more or less responsible for just transporting the data back and forth, getting data over from an RF, converting it from RF energy into an encapsulated packet, so on and so forth, until you get up to the app layer. So if you're ever looking at a Bluetooth protocol dump that we're going to look at in a few minutes, and you're getting lost looking at all these layers, remember this slide. So with that behind us, let's look at how the protocol is actually implemented in practice. You're going to have to learn a little bit of terminology, and I promise I'm not going to get super deep into this, but any Bluetooth device is called a host. And that's not my terminology, that's the Bluetooth SIG's terminology. It's a little bit confusing. And every Bluetooth host has some kind of a controller. This is a chip that is on the device that speaks Bluetooth. So in the case of your smartphone, there's a dedicated Bluetooth chip on the device. And then the upper layers of the stack, from the app layer down to L2 cap, are implemented in software in the Bluetooth stack on the device. The lower two layers, the link layer, are implemented in hardware on the controller. The way the host communicates with the controller is via an internal bus, and on that internal bus, they communicate using a language called HCI, the host controller interface. This is where we're going to sniff. And the power of this is that we're sniffing the data while it's still on the device, meaning we're going to capture 100% of the packets, and as a bonus, the encryption, the protocol level encryption happens down here. Since we're capturing at the HCI layer, if the device is using protocol level encryption, we get the data before it is encrypted. This is really powerful and really useful, as we'll see later. That's all the theory I'm going to bore you with. We'll get into the interesting part now. How does this actually work? Well, Android, Linux, and OS X have this feature, and they produce logs that can be loaded by Wireshark. Super awesome. I learned everything I know about TCP, IP, and Wireshark, and if you load up Bluetooth captures in Wireshark, you can learn everything you need to know in there too. You don't need to spend time reading the protocol manual, nothing like that. Just start dropping down menus in Wireshark, which is awesome. So on Android, if you go into the developer options menu, there is this little checkbox here, enable Bluetooth HCI Snoop Log. The Android phone running in your pocket right now, not rooted, nothing fancy, if you go into your developer options menu and check this box here, you can start logging Bluetooth from an Android app. And you can pull the data off using whatever technique you prefer. I usually use ADB because that's what I have lying around. If you're running Mac OS X, you have to have Xcode installed, and you install a package called the Xcode Hardware Developer Tools. Inside the Xcode Hardware Developer Tools, there is a piece of software called Packet Logger. It's not Bluetooth Packet Logger, it's called Packet Logger. If you run this software on your device, you can log all the Bluetooth data exactly as you can in Android. It has its own UI for doing some of that analysis. I prefer Wireshark, so you can just save the log into a Wireshark compatible format. And finally, for the Linux nerds, you guys should all be comfortable running command line commands to log this. This will output a log file in a format that Wireshark can handle. So back to the reverse engineering process, we were stuck at step 2, but now we're unstuck. We have a mechanism to capture data via Bluetooth. That means we can move on to actually doing some analysis. That brings us to our case studies. In each of these case studies, I will introduce a device and walk through the process of reverse engineering it. I'm going to start with really basic devices, and I'm going to gradually get more advanced. Now, the goal of this is to give you some real concrete devices, some devices that I actually did reverse engineering and security review on. I've anonymized them a little bit, but this is otherwise completely unadulterated. This is the exact data that I was looking at with these devices. So our first case study is a BLE heart rate monitor. This is a device that might be worn by fitness enthusiasts. They wear it on a chest strap and a strap that goes around the chest, and there's an app that runs on your smartphone, and you can log what kind of fitness exercise you're type of doing. So like if you're running or if you're riding a bike, it'll log that data and it'll log your heart rate up here. So how are we going to approach this device? How will we go about reverse engineering it? We look back at our reverse engineering process. Step 1, do something in the device, do something in the app, and make a note of what we're doing. So in this case, we're going to put on the heart rate monitor, and we're going to tell it that we're running, something like that, and we're going to make a note of this heart rate value here. In this screenshot, the heart rate is around 76. We're going to have the Android OS logging the Bluetooth HCI data in the background. Then we pull that data off of the device and we load it up in Wireshark. And I can actually give you a really quick demo of what that looks like when you actually load it up in Wireshark. If I can pop this over to the other screen. And, all right. Oh, that font is a lot smaller than I thought it would be on this screen. Okay, perfect. So if you look at this here, this is so the very first thing that you're going to see when you load up the file into Wireshark is a bunch of stuff that makes no sense whatsoever. So when I say that we're logging the Bluetooth on the device, we're logging every message that the host sends to the controller. This not only includes the data that eventually gets sent over the air, but it also includes really basic stuff that we don't care about. Stuff like setting the device name or setting scan parameters, tons of highfalutin Bluetooth stuff. Not interested in that. So the first thing we're going to do is we're going to use a filter in Wireshark, and you can't see that text there. I have it on another slide. It's BT-ATT, BT-AT. And I'll have it on the slide. You don't have to write it down now. This filters out everything and only shows you the data that is going to ultimately be sent over the air. So there were like hundreds of packets before. Now there's still like quite a number of packets, but they're a manageable number. And as we scroll down the list here, I don't know if you can read that in the back, but there's a heart rate measurement. Wireshark did all the work for us. Like, it already knows that this is a heart rate monitor. And if we go down here into the packet dissection, click this drop down, there's our value. The heart rate was 89. So maybe I was running or something when we took this heart rate measurement. What's even more interesting down here is the heart rate monitor gives us the RR interval. This is the interval between individual pulses of the heartbeat. So even though the app is only showing us the real-time heart rate information, the data being sent back by the device is even richer than we possibly imagined. So going back over here to our slides, this is the same information in case that demo failed. That's our first filter right there, BTATT. Write this down. You're going to use this if you ever look at any BLE device using this technique in Wireshark. And you can see Wireshark figured out the heart rate measurement, showed us that data. And the heart rate in this case was 82. That more or less jives with what we're seeing in the app. There's some internal consistency here. Yes, question?
Sorry, I missed your initial part. So this was the log that you get from the Android after enabling the
Yes, so the question was, where did this log file come from? This is the log file that was produced by Android that we have pulled off of the phone and opened in Wireshark on our laptop here. So the next Wireshark filter that you're also probably going to want to write down is this bthci command .le long-term key. If you see this command, that means that the host is setting an encryption key for the controller. In other words, the device is probably using BLE's built-in encryption. If you're a device developer and you see this, there you go. You know that you're using BLE encryption. If you're reverse engineering something, now you know this. If you don't see this message being sent, the device is not using the BLE encryption. Now that doesn't necessarily mean that it's not using any encryption whatsoever, but if they are using encryption, they've developed something of their own. You'll actually have to dig into the pack and take a look. For this device, they were not using encryption. So there are, it's not a medical device per se, but it is medical adjacent at least. And that means that the device is more or less broadcasting your heart rate to anybody in the room who has the capability to sniff it. And furthermore, the encryption here provides some authentication too. If this device were being used in a medical setting, it would be possible to impersonate the heart rate sensor and inject malicious heart rate values. And this could have pretty serious consequences if it was being used as part of a diagnostic treatment. What are our conclusions from this case study? First of all, Wireshark is incredible. It did all the work for us. It has a really great filtering interface, and for this particular device, it already knew how to interpret the data. The second thing, getting Bluetooth logs is practical. If you have an Android phone in your pocket right now and it has Bluetooth capability, it can do this. And using Wireshark, which is free and runs on every platform, you can interpret the data. So right now, there are practically no barriers for you to try this as soon as this talk is over. This is only a 45-minute talk. I don't have a lot of time to dig into how to actually talk to these devices. I'm going to focus a little bit more on reverse engineering them. But if you want to talk to the device on Linux, I usually use Linux to do this because it has a really rich set of tools for talking to Bluetooth. The GATT tool command is the one that I usually use. That's 3 T's in a row, GATTTOOL. And this device lets you do really basic rudimentary communication with Bluetooth. You'll see a list of UUIDs here, and most of these UUID values define services that are standardized by the Bluetooth SIG. In one case, there's a device information service, and there's a heart rate service. And I'll tell you about how to find that information in a moment. So these are standard services, and that makes sense. You would expect to see a heart rate service on a heart rate monitor. You would expect to see a device information service. But if you look down here at the bottom, there's this 128-bit UUID that doesn't fit in with the rest. It looks like a long random value. This is not standardized by the Bluetooth SIG. This is something custom from this manufacturer. And there are a couple of ways that you can go about trying to interpret and trying to talk to this device and figure out the protocol. You can start sending messages to it, and you can see what the UUID, the actual UUID of the characteristic is. The approach that I actually recommend is take that value, plug it into Google, and see if somebody else has already looked at this device. In at least 25% of the cases that I've looked at, I've either found a thread of people somewhere who have done some reverse engineering of the device, or I found GitHub repositories that have some of the white label source code that the Chinese manufacturer used. So you'll find some interesting stuff this way. Our second case study is a BLE blood pressure monitor, and I was actually talking to somebody before this talk. They have this exact blood pressure monitor at home. This device, you might be surprised to hear that a BLE blood pressure monitor exists. They're really common, actually. And this is the first case of what I like to call a Bluetooth Mad Lib. If anybody is familiar with Mad Libs from like middle school, you have to insert, like they say, select a noun, select a verb, da da da. Well, Bluetooth Mad Libs, the way it works is you select a noun and then you add Bluetooth to the beginning. And somebody in Silicon Valley is working on a product that does just that. So in this case, our noun is blood pressure monitor. This one is a BLE blood pressure monitor. You put on a blood pressure cuff, you take a measurement, and then it connects to an app on your smartphone that logs that and logs it over time. I guess there's a market for this. It's not intended to be used in a medical setting, but I know at least in one case, somebody's doctor recommended that they purchase it. How are we going to reverse engineer this device? Similar to how we did the last one. We're going to do something with the device, and we're going to log that data. We're going to make a note of what we did. So in this case, we're taking a blood pressure measurement. So you'd probably write down what blood pressure values were recorded by the app. And then when we look at the data, we're going to look for that information. I will also point out, on this particular device, the only way to get it to generate data via Bluetooth was to take a blood pressure measurement. So when I was testing it, I ended up having to take my blood pressure like 20 times in a row, which was somewhat uncomfortable. So just know that like if you're going to be doing Bluetooth testing, things might get physical fast for you. So yes, Bluetooth. In this case, I can pop open Wireshark again. Why not? Let's open another file. Okay, we're going to open our blood pressure monitor here. And again, we're using the BT-AT filter. And when we look at our data here, nothing jumps out at us. I will say the first thing to notice is that there are not a lot of packets in this file. So even knowing nothing about Bluetooth, you can start to look at this and try to get some kind of sense of what's going on here. So if we look at just take a random write request here, right? You can look, here's the data that was sent in that write request. And if you see a handle value indication here, here's some data that was sent. So even though we don't necessarily, I haven't gotten super deep into the Bluetooth packet structure or anything, but you can start to make sense of this in Wireshark. You can start to really experiment with it. And in fact, Wireshark's filtering, I'll probably, on the next device, I'll probably take a look at that more. You can really powerfully filter the devices. So when we look at this in Wireshark, the first thing I'm noticing is that Wireshark hasn't done the work for us. It hasn't already told us that this is a blood pressure monitor. So in that case, that means that we're going to have to do a little bit of legwork on our own. Excuse me for a second here. And if we look at this value here, we see something that could feasibly maybe be a blood pressure measurement. It's the only packet in the capture that's kind of long. And if you look at the Bluetooth SIG's website, you'll see that there is a blood pressure service. However, this device is not using that. And this is actually extremely common. This is our first instance of what I'm going to call a hidden serial port. And for those young gamers in the crowd who aren't familiar with the serial port, it is a bidirectional communication mechanism. You send data one way, you get data back the other way. Why do people implement things this way when there's perfectly well standardized profiles for doing this? My thinking on it is that Bluetooth is complicated and weird, and if you're a hardware developer, you just want to get on with your day. You want to get data wirelessly. You don't really care about the details. You don't want to get into the deep, fancy Bluetooth stuff. This is the first time we've seen this. It's not the last time. In BLE, it's implemented using a write characteristic and a notify or an indicate characteristic. And this is handy because you can always tell which direction the data is flowing. The write characteristic is data that goes from the phone to the device. The notify characteristic is data that's coming back from the device to the phone. Going back in here, you can see handle value indication. That's a notify characteristic. That's data coming from the blood pressure monitor back to our smartphone app. That makes sense now. This is probably a blood pressure measurement in here. And if you look inside those values, these are like the second, third, fourth, and fifth bytes of the packets. To my eyeballs, this looks like a little endian 16-bit value, and this looks like another one. And if you turn those into regular decimal integers, you see it's 117 and 81. that exactly matches with the value that we saw. And at this point, you can start to make sense of the data, the structure of this data here. And one thing that's interesting is that there are quite a few more bytes that go on past that. If you're reverse engineering this and trying to hack it and all you care about is the blood pressure measurement, you're done. However, if you want to actually learn more about what some of these other bytes do, where I normally start looking at this point is the app. Android app reverse engineering is definitely out of scope for this talk, but it's super easy to get into it. Just Google it. Long story short, you can get back something that more or less resembles Java. And in this case, even some of the string values were preserved. So taking the UUID values that you might get out of GATTool, searching for those inside the app, you can see, oh, there's a blood pressure measurement characteristic. And you can actually see a bunch of other stuff like firmware update service, for instance. That might be interesting. And if you look at the code that references this data, you start to see really useful log messages like received blood pressure, received timestamp, motion detected, and irregular heartbeat. This one was really interesting because I could simulate motion detected. I could simulate different blood pressure values. I don't have an irregular heartbeat. I couldn't possibly simulate that. So the only way for me to get this information is to look in the app. Security-wise, what did I find on this device? Well, there's no encryption, so that's already a concern. So you're already leaking what could potentially be patient medical data, depending on the context in which this is used. Furthermore, on this particular device, I found that there was another characteristic or another service that was a firmware update service. Anybody who figured out how to communicate with this device, for instance, by looking at the app, would be able to send malicious firmware updates to the device. Once again, not actually a medical device, but who knows if it's being used in a medical setting or not. The consequences of setting incorrect blood pressure data could be massive. What are our conclusions here? The hidden serial port. Again, this is not the last time we're going to see this. It's extremely common. Once you get past the weird Bluetooth stuff, it's just normal binary reverse engineering. And finally, when in doubt, look in the app. Security-wise, no encryption, and there's a firmware update service exposed. Imagine you are the Bluetooth device developer. You want to know this yourself before somebody else figures out about it and writes a mean blog post about you. All right, I'm going to pick up the pace a little bit. BLE Padlock, somewhat self-explanatory. It's another device kind of aimed at the fitness market. You go to the gym, you put this on your locker. It has an app that runs on your smartphone. If you want, you lock your locker, you walk away. At the end of your workout, you pop open your smartphone, you click unlock. How do we reverse engineer this? Step 1, unlock the lock. Step 2, look at the data that comes off the device when you unlock that lock. And you'll never guess what we find on this device. It is another hidden serial port. So if you look at this data, this one is where things start to depart from the previous ones. We see something that's happening over this hidden serial port, but it's looking a lot more opaque. This is just a bunch of long random binary data. And going through these packets, there are like lots of these weird binary messages. And this is where you start to hit the limits of Wireshark as a tool. It's not really great for doing a lot of comparative looking at messages that are sequential. And fortunately, Wireshark provides a really powerful feature that allows us to get at the data a separate way. If you go into the file menu, export packet dissections as JSON, you get a complete JSON dump of all the totally decoded packet information. This is awesome. Any modern programming language ships with a JSON parser, and you can load this data in that way. Or if you're like me, you'll write some super grody regex-based parser in Perl. Don't judge me. Only God can judge me. And by God, I of course mean Larry Wall and his glorious mustache. This is what the output of that tool looks like. And this is a custom tool that I wrote, but it's really only like a few dozen lines of code. All it does is take in JSON and prints it out. Now what we're seeing here at least makes a little bit more sense in terms of like our ability to look at it. You see a bunch of like binary strings, then you see this value here. This is actually 128 bits long. Now we're starting to get into seeing stuff that looks like, well, maybe this is an encryption key or an encrypted block. And it's really hard just looking at this data to make any sense about it whatsoever. In this case, you really have to go into the app, look back, and see how it works. What I found in this particular app is that they were using encryption that was, so you trace through the Java and you end up getting bumped out to a native encryption library that's shipped with the app, written in C++. This is where I gave up and I said, it might be secure, it might not be secure, but I don't personally have the time to go and reverse engineering this custom encryption algorithm. And that's actually one of the takeaways I would give to you is custom encryption is really common, and implementing custom encryption is fraught with peril. It is not something to be taken lightly, and a lot of companies do take it pretty lightly. You can't just slap together AES and a couple keys and say you're done. Like if you're really thinking about doing some custom encryption, please hire a cryptographer. Don't let your programmers do it. They know just enough about crypto to be dangerous. What are our conclusions on this? The developers were at least security-minded. They tried, they're using encryption, but is the homegrown encryption good or not? I don't know. I didn't take the time to look. It's not as bad as some of the other BLE padlocks I've seen out there. There was a DEF CON talk a few years back destroying a bunch of these, but who knows? I'm going to pause here and take a brief intermission because I need to grab a sip of water. But are there any questions before I move on? No questions. Okay. I'll awkwardly grab a cup of water here. What have we seen so far? First, reading data going to and from Bluetooth is straightforward. Really, it's simple. You turn on the HCI logging in Android, you do stuff in your app, you pull the data in, and Wireshark can interpret the data for you. And if you run up into limits on Wireshark, you can export the data and parse it in your favorite programming language. Number two, no encryption on the first two devices. Huge target, and given the context in which they're used, privacy implications and possibly patient health implications. Furthermore, firmware updates. It's like I said at the beginning, security in Bluetooth is kind of the Wild West. Fourth case study, a classic Bluetooth headset. It's not exactly a headset. It's an industry-specific device that works more or less like a headset. And just think of it in your mind as a Bluetooth headset. There are standard profiles that most Bluetooth headsets would use. One is called A2DP. This is the profile that if you've ever used a Bluetooth speaker or Bluetooth headphones to listen to music, you're using A2DP. The other is HFP, hands-free profile. If you're making Bluetooth phone calls via Bluetooth in your car or on a headset, you're using hands-free profile. Once again, they're not using these. There is another custom serial port. Why is there another custom serial port? Well, reasons. They're actually somewhat pretty good in this case. This is a classic Bluetooth device. This is not a BLE device, and that helps us to a certain extent because there's already a profile in classic Bluetooth for speaking as a serial port, the serial port profile. Meaning, when we pull the data into Wireshark, now all we need to do is filter on, it's called RFCOM here, but that means serial port profile. So that saves us at least some of the trouble of having to look at the data and do fancy Wireshark filters. Fun fact, the best Wireshark filter to use if you ever have a serial port profile device is the word data, D-A-T-A, data. It just worked out well in this case. And again, we can page through this data in Wireshark, and if you pay attention to the bottom of the slide here, you can see the data changing between these values. And Wireshark is not the best for doing this type of analysis, but in this case, we actually can do some rudimentary analysis in Wireshark, and we see a structure emerging. Every packet starts with this magic number, followed by an opcode, a sequence number, a 16-bit little endian length, and data, and a checksum. And this is enough to kind of get us a broad sense of how the device is communicating with a companion app, but it's not enough for us to really make a lot of sense about it. Again, in this case, we're going to export the data to JSON using a homeopathic application of Perl or your favorite programming language. You can build a tool that looks something like this. In this case, I've got a little direction indicator and an opcode, and you can start to see these big data patterns emerge. Knowing the nature of this device, when I see it's a headset, right? There's going to be audio data. And I'm seeing these big blobs of binary data here. This is probably audio data. So I hacked together the tool a little bit to export these big blobs of data into raw files, and then turned over to Audacity, an open source tool for processing audio. You import the audio, you have to specify all these values. So in this case, it was signed 16-bit PCM, big endian, 1-channel mono, and 4,000 kilohertz, 4 kilohertz sampling rate. How did I know these values? Let's call it an educated guess. But in reality, when it comes to audio, they're only, like, if you just play around with these values a little bit, you'll eventually end up with something that looks like this. This is an audio file. And in fact, when I played it back, it was a very low sample rate recording of my voice saying this is a test. What do we take away from this? First, that the techniques that we use for BLE devices work equally well for classic Bluetooth devices as long as you have a companion app. In this case, I neglected to mention it. The companion app runs on Linux, but if you just run the btmon command, you can log that data and load that into Wireshark. How much of what we were talking about was actually Bluetooth related? Almost none of it, right? Ultimately, this really boils down to basic reverse engineering. Finally, because it's classic Bluetooth, the device is essentially required to use encryption. So in this case, there were no flaws with the actual encryption of the device. However, I didn't dig into it. It might be possible to do some sort of a buffer overflow attack on the device by messing with length data, memory corruption, that sort of thing. Or for that matter, in the companion app that runs on the system. Now is when things start to get a little bit more interesting. I'm going to be talking about a BLE credit card. Absolutely a case of a Bluetooth Mad Lib. What is a Bluetooth credit card? Pretty simple. You have a credit card, you slap Bluetooth on it, and it's supposed to replace your big fat wallet. This particular device, the way it works is that you load your credit card number into a smartphone app. It sends your credit card over Bluetooth to the credit card. It sends your credit card number over Bluetooth to the physical credit card, and then you use buttons and a screen on the device to select which Bluetooth credit card or which credit card you want to use when you make your next payment. I hope most of you, your toes were curling when I said you send the credit card over Bluetooth, because that was immediately what brought me my interest on the device. Not really apropos to reverse engineering the Bluetooth part, but I went and talked to my pal John McMaster, and I said, how the hell do you fit a Bluetooth into something that's the size, shape, and thickness of a credit card? And he said, well, let's look at it on an X-ray machine, because I have one of those in my garage. And this is what we came up with. I don't have time to dig into all the details of it, but it is, if nothing else, it is an extremely impressive technical achievement that they were able to fit all this technology into something the size and shape of a credit card. And what is even more shocking to me is that not only one company does this, there are actually a total of 3 companies that are currently or previously made a Bluetooth-enabled credit card. This is the only one I've seen that has a rechargeable battery, which, again, blew my mind that you can make them that thin. But anyhow, same reverse engineering applies. Load credit cards into the app, send them via Bluetooth, and look at the data in Wireshark. The first thing, bravo to this company, they are using BLE's built-in encryption. You can see we've got the LE long-term key command here, start encryption, and this is our actual encryption key right here. Now this is, don't freak out that you can see the encryption key. This was logged on the device that we control. However, this is the actual encryption this is the key that's being used to encrypt the data. The data itself, as mentioned before, is logged before the encryption is applied to it. So now, even though if we tried to log this data over the air using a Bluetooth sniffer of some sort, it would just look like encrypted garbage to us. But we can analyze the protocol here in Wireshark because the encryption hasn't happened yet. And we can see something that amounts to another hidden serial port, surprise, surprise. And if you start to look in the decoded protocol here, there's actually some ASCII data. So that's good. This is not really even binary reverse engineering at this point. This is a protocol that we can really make sense of. So exporting the data into JSON and writing another basic Wireshark parser, exporting the data into JSON and writing another parser, you can see you get a bunch of messages, and they all have a really predictable structure, and you can even start to see some unencrypted data, or well, it's not encrypted yet, some ASCII data here that one of these is a fake credit card number that I injected into the app. So now you can actually see the credit card data that's being sent over Bluetooth and start to make sense of this protocol. This byte is always fixed. This byte is high entropy, and it's at the very end. That's probably a checksum. We see a single byte here, probably something like an opcode, something that looks like sequence numbers, and a bunch of data. Well, guess what? This is what the message format ultimately ends up being. And I think what really surprised me was seeing these ASCII lengths encoded in these lengths encoded as ASCII values inside the protocol. That tells me that some parser somewhere is looking at that length. And anytime I see a length value embedded in a string, I'm immediately wondering what kind of mischief you can cause with that. In this case, I didn't find any sort of mischief like that. You might be thinking, well, they used encryption. They were safe, right? They were not safe because they were making assumptions about how BLE encryption works and how it kept them safe. In this particular case, if you gain physical control of the credit card, for instance, if you're a waiter at a restaurant and they hand it to you to pay a bill, you could unlock the device and you could actually extract credit card numbers from the device. So I think the biggest takeaway I want you to take from this is that encryption is not a silver bullet. You need to fully understand your threat model and understand all the possible ways your device can be abused. Our conclusions here, though, HCI logging allows us to see encrypted data. Even if the data is encrypted via BLE encryption, we can get the data here. The encryption is not a silver bullet. Finally, our last case study, I only have a few minutes left, a BLE Electric Skateboard. This is 100% a Bluetooth Mad Lib, and I 100% support it. These things are awesome. There's one wrench in the gears here. There's no app, or at least at the time that I tested this. And this is actually some joint work that I did a few years ago with Richo Healey. There is no app. So the only way that you can get any data via Bluetooth is using this handheld remote controller. This is just a hardware device that you hold in your hand, and there's a little wheel here. When you adjust the wheel, it adjusts the speed of the motors on the skateboard. In this case, since we don't have an app, the technique that we used for the previous 5 case studies won't work. You have to use a sniffer. In this case, we're going to look at using an Ubertooth. And here's where the reverse engineering process deviates a little bit, and mainly due to limitations of the Ubertooth. The first thing we're going to do is launch the Ubertooth as a sniffer. We're going to connect the remote control to the skateboard, and if the connection is not captured by the Ubertooth, you go back to 1. You just keep doing this in a row. And it can take like a couple tries, like maybe sometimes a couple dozen tries to actually get it. But once you finally capture that connection, you do stuff with the board. Like you adjust the speed, you let go the dead man switch, and see what kind of data gets generated. Finally, pull that into Wireshark. Just to give you forewarning, if you're going to try to do this, you're going to need at least 3 Uberteeth to reliably capture every connection. You can do it with 1, it just means you're going to spend 3 times as much effort. And in my experience, more Uberteeth is better, so just go ahead and go out and buy a bunch. When you load the data into Wireshark, we again see our hidden serial port, and what's interesting here is that we can see some ASCII protocol data. In fact, it is almost literally a serial port. It even ends with a carriage return character, which is a little bit bizarre for a hardware device. One other thing that might shock and terrify you is that there is no encryption on this data. This is captured raw over the air. If there were encryption, we would have seen it by now. So, protocol reverse engineering. Here is a sample of some of the messages that were sent, and if you correlate them back to what was happening during the capture at the time that the messages were captured, this is what happens when it just connects and it's idle. Well, as soon as you press the dead man's trigger, this value here changes. And as you increase the throttle, the speed goes up. The only thing that really kind of gets in the way of just injecting whatever speed you want is that this value here at the very end turns out to be a really simple checksum. It's a like AND together all the nibble, or XOR together all the nibbles of the speed command for some reason. I don't know why they did that because there were already checksums built into BLE. However, there's no encryption, which also means that there's no authentication. The protocol is very simple. In this case, it's only a small matter of programming to write a tool that impersonates the Bluetooth remote controller and injects whatever speed command you want into the skateboard. Richo and I actually got a CVE for this, and as far as I know, is the only only skateboard-related CVE that's out there, and it's one of the few CVE descriptions that includes the wording, "This use of this CVE may result in harm to the rider of the skateboard." So I'm saying it a little bit light of a tone, but there were real actual consequences to this. Until they fixed the problem, somebody could have hijacked skateboards and caused people to fly off. This is a thing that actually happened because we spoke to the developer after we reported this vulnerability, and they said, well, we were following the hardware manufacturer's guidelines. We set the flag that said to use encryption, but they never verified it. All they would have needed to do is spend a few minutes with an Ubertooth, and they would have immediately found out there was no encryption and they were at risk. Conclusions here. Ubertooth, much harder to use than HCI logging. If you have an Ubertooth or you're thinking about using an Ubertooth, see if you can use the HCI logging feature first. If the device was using encryption in this case, we would have to crack the encryption. And I've released some tools in the past in order to do that. And I should have added a bullet point for this, but if you're developing a device and you think you're using encryption, make sure you validate that. End-to-end testing is the only way that you can possibly validate it. Parting thoughts, wrapping things up. What are the most common security problems that I've encountered? Devices using no encryption. We saw it in 3 of our 6 use cases, and 50% of devices pretty much reflects what I've seen out on the market. There are problems with homemade encryption. We didn't really see it so much here, but many of the times that I've seen devices that use custom encryption, there's some kind of an encryption flaw. Be it reuse of a key, improper use of algorithms, all sorts of stuff. Be very, 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 very careful if you're implementing custom encryption. There were some debug interfaces on some devices that I've encountered, and incomplete threat modeling. This is what tanked the Bluetooth credit card. They were using encryption. The app and the design were reasonably well thought out. There were just a few corner and edge cases that they didn't consider. So security, you have to be holistic about it. You can't just think, oh, I'm using encryption, done. You have to have a big picture. Conclusions. Doing this is affordable. You don't need to drop $20,000 or convince your purchasing department to approve the invoice. You can use hardware that you already have. And the reverse engineering process and tools are very straightforward. You can use an Android device. You can use Wireshark. You can even export data from Wireshark. And finally, by studying these case studies, I hope you've gotten a sense of how to actually approach them in concrete terms. Any device that you encounter is probably going to be at least the rudiments of the reverse engineering are at least going to be very similar to the ones we've already discussed. And I'm going to leave you with a call to action. Go forth and hack some Bluetooth. You probably have an Android device or have access to one. Go try this out. They're in the Bluetooth CTF, or the hardware CTF right now. There are Bluetooth devices that you can use these techniques on. I'm going to be hanging around there this afternoon. Come try it. Come ask me if you have problems. And that's it. Are there any questions?
Do we have questions?
One up here.
For the Bluetooth credit card, was there anything that could be captured via Bluetooth that couldn't be captured otherwise by the mag stripe or the smart card chip?
Well,
It looked like there was a string or something, but I don't know if that was on the other interfaces.
Yeah, so the actual data that was sent via Bluetooth, I think it was the track 1 data and a few other pieces of information, but it was essentially equivalent to what you would have gotten off of a mag stripe card or swipe or whatever they call those things. This device had a smart card built into the PCB, but it was not exposed to the outside world. So I think it was something that was on their Rev 2 board that was supposed to come out, and I don't know if that ever came out. Does that answer your question? Other questions?
Thank you. So the idea of using Android and your phone and going above the layers, the link layer, that is when you are the device that paired with a Bluetooth device.
Yes.
What if there's a device that paired with another phone and you're the bystander? In that case, do you have to go to a sniffer? What's there?
So you're asking if you want to sniff somebody else's Bluetooth?
Yeah.
You have to use a sniffer.
Yeah.
And in the case of BLE, you can try your luck with an Ubertooth. I found in practice, if you're not controlling one of the devices, it's pretty hard to actually successfully sniff. You have to capture the initial part of the connection. And if you miss that, yeah, it's troublesome.
Have you found that initial handshake for the pairing to be vulnerable if you were there to sniff?
So if you're referring to the built-in BLE encryption, the LE legacy pairing, which is what most devices still use if they're using BLE encryption, is in fact vulnerable to an encryption attack. A few years ago, I gave some talks on that, and there's a tool called Crackle that you can look up. It should be linked from my website here. I will say that at the time, I think I overstated the danger of using built-in encryption. The pairing process is weak only at the time of pairing. So let's say you paired your devices at home, then you go out to a coffee shop and use the encryption there. There's no real risk to the encryption. The only time you're vulnerable is at that moment when you initially pair the devices. Other questions?
Any other questions? Okay, that should be it.
Right.
Thank you.
Thanks.
All right, so we'll break for lunch and we'll be back at 2. The lunch is